Hi everyone, welcome to CS188 exam prep number 10. My name is Ryan and today's topics are going to be naive Bayes and the perceptron algorithm. So let's just dive right in. So in question 1, we are given a problem where we are standing in an exit and either Pac-Man or ghosts come out of it. And every time we see someone or hear someone come out, or every time someone comes out, we get some sort of observation cue. So either visual, where we see them, or an auditory one, where we hear them. And those are represented by these two variables, xv and xa respectively. And from those variables, or the results from observing those two things, we can sort of determine some sort of gauge over whether or not the person or thing coming out is either a Pac-Man, where it's equal to 1, or a ghost if it's equal to 0. And both of these observations are independent of each other. And you just like, if you see something, you might have some cue that it's a Pac-Man or a ghost. Or if you hear something, you might have a different inclination of the same thing. And we also classify each sample essentially as by their actual type. So this yi is the actual true type of the thing coming out. So either actually a Pac-Man or actually a ghost. And we've observed the first 20 individuals and logged their individual observations here. So for example, what this means is that at time step 0, this is like the first character exiting. And our visual cue told us that, oh, this character is a ghost because ghost is equal to 0. Our audio cue told us that based on our hearing, the character coming out is also a ghost. And the actual type of the character was a ghost. So those are just like how you would read these individual samples. And that repeats for 20 characters that are exiting. All right. And so just some notation right here. We have that the superscript I determines that the datum is the ith one, and then the individual, if I equals 20 comes out, you want to predict the individual's type, y20, given that you observed xv20 equals 1 and xa20 equals 1. So basically, we have all this old data, and now for the next individual that comes out at I equals 20, so the 21st character, we want to be able to predict the actual type of the character, given that we observed this xv20 equals 1 and xa20 equals 1. And so right here, since we're assuming that the types are independent and that the observations are independent conditioned on the type, we can model this using naive Bayes. And naive Bayes is basically a way to model classification problems, essentially making this large assumption that all the features are independent given the class label. And that is why it's called naive, because it's not necessarily true, but it is something that greatly simplifies the way that we do calculations. So we assume that the x's are the features and that the y's are the labels. And what we also have are these probability distributions, where we have that the probability that xv is equal to little xv at any time step, given the yi is equal to some little y, is going to be these associated probabilities. And then the same for the auditory with these associated probabilities. And that we have the probability that any y is equal to 1. So any actual true type of the character is equal to Pac-Man is going to be q. And all of these are between 0 and 1 just to create valid probabilities. Okay. So the first part of this question asks us, what is the maximum likelihood estimate of PV, PA, and Q? And really all it's asking there is kind of just asking you to, in terms of naive Bayes, maximum likelihood estimate, all it asks you to do is basically take the count over the total. And so what does that mean in terms of this problem? Well, for example, right here, we know that PV is going to be the value right here, which is associated with the case where XV is equal to Y. And so what that means is, let's say we have all of these samples. We have 20 different samples. To calculate what PV is using maximum likelihood estimation, all we need to do is count the number of samples up here that follow this specific condition. So all of the values where xv is equal to y. And then we take that over the total number of samples that we had. And that will give us our maximum likelihood estimation. So in the general case right here for naive Bayes, really all that we're asking for is for you to take the count over the total. And there's like a long derivation of this in the notes whereby you do some like fancy probability formulas. But I encourage you to read about that afterwards, because the derivation isn't necessarily in scope, but it might be good for your understanding. So going off that, if I want to compute PV, what I can do is count each of the samples whereby xv is equal to y. And so going off that, I can see like here 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 0, 0, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 0, 0, 0, 0, 0, 0. So that is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So that's 16 out of a total of 20 samples, which means my answer is 16 over 20, which is equal to 4/5. Now I can do the same things for PA and Q to get very similar results. So for example, if I use a different color, let's say for PA, I'm trying to figure out all of the cases where XA is equal to Y. Well, for XA is equal to Y, what I can do is I can do the exact same thing, except I'm going to be looking at like these two columns at a time. So let's do it. 1, 2, 3, 4, 5, 6, 7. And then these are all different. 8, 9. These are all different. 10, 11, 12. So that's 12 different samples over a total of 20. So that is 12 over 20. And then simplifying, that gives us 3/5. And lastly, for the case where we're looking for Q, we're just taking the count of where the true label is equal to 1 and dividing that over the total. And so for this one, we just look at the last row right here, right? Because that's the only thing that contains the true label. And then we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that gives us 10 over 20, which is equal to 1/2. And those are the values that we would get given our current observations. All right, cool. So now the next part of this question asks us, what is the probability that the next individual is Pac-Man given your observations? And then we want to express our answers in terms of these parameters, PV, PA, and Q from the previous part. So we can do this by looking at what we want to compute and then seeing what we have to work with and then figuring out what we can do to like kind of work our probabilities that we have into this conditional distribution. And one thing that you might want to recall is that for conditional distributions, one good way to start off is by doing something with Bayes' rule. So what Bayes' rule tells us is that the probability of A given B is equal to the probability of A comma B over the probability of B. And so we can do something very similar here, except using the probabilities that we have instead and substituting A and B appropriately. So let me just shrink this down, put this on the side. And so if we're looking for the probability of Y20 equals 1, given XV20 is equal to 1, and XA20 is equal to 1, well, this is the same thing as taking the joint distribution of all those variables. So Y20 is equal to 1, XV20, is equal to 1, and XA20 is equal to 1, and then dividing by just the probability of everything on the right. So that's the probability of XV20 is equal to 1, and then the XA20 is equal to 1. Okay, so now we can use our values in our distribution at the top right here, to be able to plug in values and then kind of figure out where we're at. So I'm just going to make a new page for space. And so now suppose that I start with the top. Well, the top is just the joint distribution of all those things. and following the Bayes net property, where if we just multiply the CPTs together, we would get the joint distribution. We can essentially multiply the associated probabilities from our distribution to get our top value. So what does that entail? Well, we're multiplying each of these for the cases that match the conditions that were given. So the conditions that were given are that y20 is equal to 1, xv20 is equal to 1, and xu20 is equal to 1. So that means all of the labels are equivalent to the features. And in that case, we're going to take the appropriate columns. So right here, y is equal to 1 corresponds to q. Corresponds to q. Xa is equal to 1, which is equal to y, corresponds to PA. And xv is equal to 1, which is equal to y, corresponds to PV. So multiplying all that together, that means my top is just going to look like PV times PQ times A. Now this is divided over the joint probability of just xv equal 1 and xa equals 1. And to get that, we can use the law of total probability to sum out the variable that we don't need from the top, and then just get the joint distribution of the bottom. So recall that the law of total probability says that if I sum over some variable a of probability of a comma b right here, so that's the joint distribution of a and b. If I sum out a, I can just get the probability of b. So I can do the same thing here, where I can sum out the probability, or I can sum out the variable y20, and then just get the probability in terms of xv20 and xa20. So doing that, what that means is, for one case, I have I have PV times PQ times, this is not a Q, this is an A. PV, PA, and Q. So that's the same as the top, plus what happens in the case where y is not equal to 1. So we're summing over the possibilities of y. So this is the case where y is equal to 1. Now we want to add the case where y is equal to 0, since those are the two possibilities of y, and we're summing that variable out. So in that case, if we take a look at our probability distributions up top, what we have is, in the case where y is equal to 0 and the features remain the same, we actually have 1 minus q right here. And for the other cases, we need to take into account the fact that y is no longer equal to xa or xv. So that means we're taking this value right here, 1 minus pa, and this value right here, 1 minus pv. So overall, that comes out to 1 minus pv times 1 minus pa times 1 minus q. And so this would be the answer. So for part B, this time we are given some slightly different information, where instead we have buses, and we have individuals coming out of a bus, and each bus can carry exactly 9 individuals. And basically the goal is to essentially figure out the type of the next individual given all this previous observations. And the difference here is that we have a slightly different probability distribution, where instead of probability of just y, we now have the probability of y given z. So y equals 1 given z equals z. And we have the probability of z equal 1, where that is equal to just r. And once again, all of our variables are just between 0 and 1. And essentially how we would read these observations at the top is, we have the same visual and audio cues right here. We have the same type, the correct type of the individual right here. And we also have the corresponding bus that each segment or each partition of 9 individuals can actually take or are on right now. So for example, the first 0 through 9 are on bus 0, and the corresponding bus type is going to be 0. And similarly, for the next 9 people, they are on 1, which has a bus type of 1, and so on. All right, great. So moving on to the actual problem, we are asked to basically compute the maximum likelihood estimate of Q0, Q1, and R. So between this and the first part from part A, not much has changed, because all we really need to do to calculate the maximum likelihood estimate is to take the count over the total once again. So for Q0, we see that this corresponds to this probability distribution with this value, where we look at the case where z equals to 0. And we see that Q0 is going to be the corresponding probability of y is equal to 1, given z is equal to 0. So looking at that, we can look at the bus that is z equals to 0, which is this one right here. And then we need to count the total number of true labels that are equal to 1, given that we're on that bus already. So in this case, we can see that this corresponds to these two, which means that our maximum likelihood estimate is these two over the total on that bus, right? Because we're calculating something given something else. So we're calculating the probability that y is equal to 1, given that we're on this bus z equals to 0. And so therefore, if we take the count over the total, that comes out to just 2 over 9. Because there's 9 characters on that bus, and 2 of them are y is equal to 1. Now, similarly, we can do the same thing for Q1, where instead right here, we have this corresponding probability, Q1, where z is equal to 1. So instead, we look at this bus right here, and we take a look at all the cases where y is equal to 1, given that we're on this bus. So that is 1, 2, 3, 4, 5, 6, 7, 8. And so correspondingly, that comes out to just 8 over 9. And now lastly, we are asked to calculate the probability of z is equal to 1 is equal to r, right? Because we're trying to figure out what is r using maximum likelihood estimation. And the way we look at this is same as before. We take a look, okay, so the probability here, z is equal to 1 is equal to r. So we need to figure out of the buses, which buses are 1 and which ones are 0, and then take the total, take the count over the total. So we see that there are only 2 buses, 1 is 0 and 1 is 1. So that means out of the 2 buses, only 1 is consistent with this case. So our answer right here is just 1 over 2. And so you see the difference right here is that before we were calculating based on this smaller sample space, because we set our sample space to be z. But in the other case, for where probability of z equal to 1, our sample space was larger, and so we took the value or the associated count of the total number of buses. All right, so let's move on to the next part. And so in the next part, we are asked to compute the following joint probability. And we want to simplify our answer as much as possible, express it in the previous parameters. So right here for convenience, I've copied down the values within the probability distribution. And now we're just asked to calculate this joint probability. And what we can notice is that this joint probability is the same thing as taking all the variables and getting their overall joint probability, except we summed out the value of z, where if we notice z is not in this joint distribution. So basically what we would have to do is we can form the same joint distribution and then sum out over the values of z. And to do this, what we can do is write this using the law of total probability and an application of the chain rule, where, for example, I can write this as the sum over z of each of these distributions multiplied together, correspondingly based on our observations. So this would become probability of y20 is equal to 1, given z2 is equal to z. Probability of xv20 is equal to 1, given y20 is equal to 1. Probability of y19 is equal to 1, given z2 is equal to z. The probability of y18 is equal to 1, given z2 is equal to z. The probability of xa20 is equal to 1, given y20 is equal to 1. And lastly, the probability of z2 is equal to z. So if you're not sure how I got that, all I did was for each of these variables within this joint distribution, I just multiplied their associated individual distributions probability together. And then I just took all those, I took the product of all of that, and then basically at the end, we sum out over z to get our answer because we have the total joint distribution and we just want to get rid of that variable. All right, and then so simplifying this further, I can split this into the cases where z is equal to 1 and z is equal to 0, and then plug in the appropriate values accordingly. So for the first case, let's consider where z is equal to 1. Then we would essentially get r times q1 times PV times Q1 times Q1 times PA. And so that comes from taking each of these corresponding expressions, plugging in the value z is equal to 1, and then selecting the value from each of these probability distributions to get the answer. So for example, let's say when I plug in z is equal to 1, right here, I want to basically figure out the value of this first conditional probability. I have probability of y20 is equal to 1, z2 is equal to 1. And then that just corresponds to Q1, reading it straight from this distribution right here, because we see that this is the case where z is equal to 1 and y is equal to 1. And so that's where those values come from. I can do the same thing with where z is equal to 0. And I would get 1 minus r times q0 times pv times q0 times q0 times pa, using the same steps. And then lastly, all I have to do is add them together and then kind of maybe simplify if I can. So this becomes just r times q1 cubed pvpa plus 1 minus r q0 cubed pvpa. And then factoring out the pq or the PAPV, I get PAPV times q0 cubed times 1 minus r plus q1 cubed times r. And that would be our answer.